So there is one more problem which we need to analyze. The problem is about a power transistor operating in the class A in the circuit shown in is to deliver a maximum of 5 watt to a 5 ohm load. So now we will be drawing the power transistor. So I think this is the transformer coupled. Uh, I have not shown in the figure, but I'll try to draw. So in the transformer coupled, you can see that there is, just a minute, uh, there is a transformer here between the DC biasing voltage and the collector terminal. So there is a transformer coupled. This is the primary winding. This one is the secondary winding, and our we have shifted our load resistance from primary to the secondary. So this is RL. Now that is the collector terminal. This is the collector terminal. Okay. This one is the okay. This one is the base resistance. Sorry, this one is a resistance, not the base resistance. This is the combination of R1 and R2. Normally, we use the uh, what you can say the voltage divider circuit for the stable operating of a transistor. So we can call it as the R, let us say, and this one is the input voltage. This is the emitter. Fine. So what it is saying that this transformer coupling is delivering the maximum power of 5 watt to the 5 ohm load. So what is given, that is PAC maximum it is given. So when it is PAC maximum, this is the maximum value, we can say that is Vrms square upon RL. So Vrms square is what? Vm upon root 2 whole square upon RL. Actually, this is the maximum power. That's why we have written voltage in the maximum form. So this is Vm square upon twice into RL dash, because we are very much concerned about the primary side. This is the actual load resistance we are going to reflect here. In the last class, I told you this is the R1 upon R2, N1 upon N2. This is the relation between the actual load impedance and the reflected load impedance. So, what is the right? So this one is VAC maximum, and right, this is a VCC. So we will have to calculate the VM value. Now, how you are going to calculate the VM value? This is a transformer coupled. So in the transformer coupled, your coordinates will be like this. This is IC and VCE. Okay, so maximum voltage will be twice VCC, and this one is twice IC, and the operating point is located at the middle of the DC load line, that is IC, and this is VCC. So VM, if you are going to impress uh, the AC voltage here, okay, this is the reflected VCE. I have drawn like this. This one is the IC. So you can see this is a peak to peak value. Peak to peak value is twice IC, or you can see peak to peak value of VCE is twice VCC. So what is the peak value, which is the maximum value? So VM will be equal to VCC, and I think VCC is given 20 volt. Minimum value is 0. So 0 minimum value is 0. So VM will be equal to VCC, and that will be equals to 20 volt. So Vm square is equals to 20 square. Why we have taken Vm as 20? Because Vm will be equal to VCC, and so this is twice into RL dash, and the BAC maximum will be 5 watt. So I think you can easily calculate this 2 into 5, that is this is 400 upon 10. So 40 ohm is the reflected load impedance. Fine. So I think you can easily calculate the reflected load impedance. So now you are having this 5 ohm. This is 40 equals to n1 upon n2 ka whole square into RL. Actual load impedance is always given in the problem. So this is the 5 ohm, right? And so you can easily calculate now the n1 upon n2. You can see here, this is n1 upon n2, 40 by, I think this is 5 ohm. Somewhere I did the mistake. This is 40 upon 5. This is 5 ohms. Sorry. So this one will be 8 ohm. So this you can calculate easily. Fine. Okay. So I think this one is over. Okay, so you can easily calculate the turns ratio. The only mistake which I did while preparing the notes, that I have taken RL as 4, but you can see that in the problem only it is 5 ohm load. No? So 5 ohm load is the actual load impedance. Now what is the peak collector current? Peak collector current is IC only. Na? Peak collector current is IC only. So you can easily calculate peak collector current. So peak collector current means what? When peak voltage will be applied upon, this is RL dash, RL dash VCC upon, because why we have taken RL dash? Because everything is on the second and in the primary only. Na? So VCC upon RL dash. So 20 upon how much I got, that is 40. I think right. So this is the value 40, that is 0.5 ampere. See, RL dash equals to, what is the quiescent operating point? Why? So you can easily calculate, because you have calculated the okay. Let us say we will again draw this. This is quiescent. This is twice IC. This is twice VCC. The operating point will be IC and VCC, which you have already calculated. This is the IM value. This is the VM value. Fine. Now the collector. Now to calculate the collector efficiency, how you are going to calculate the collector efficiency? So collector efficiency will be equals to, PAC upon PDC. PAC is given, that is 5 watt. PDC is unknown to you. Similarly, efficiency is to be evaluated. So PDC will be equal to VCC into operating point. That will be ICQ. We can say IVCC into IC. Now VCC will be equals to 20 and IC will be equals to, right, IC will be equals to IM. Then Im will be equals to 20 upon 40. You can see Im will be equal to VCC upon RL dash. So this one will be 400 upon 40. That one will be 10 watt. Fine. So you can see that 5 watt upon 10 watt. Okay. I think this is clear to you or not. This one is 400 upon 40. That one will be 10 watt. So PDC will be equals to 10 watt. Fine. So 5 upon DC value is 10 watt. 5 upon 10. That will be 50% efficiency you have obtained. You can easily obtain using this power transistor. I think everything is easy only. No need to panic. You can say 50% efficiency, right? Now you can see there is no transformer coupling in this class A power amplifier as such. So this is the normal class A power amplifier, or you can say this is direct coupled class A power amplifier, where beta value is given. Fine. And where is the quiescent point? Quiescent, which means the operating point. So this is VCE and this one is IC. Suppose if I will plot like this is VCC. Then this one is right. VCC upon RC. VCC upon RC. So what? So according to you, what is the quiescent operating point? ICQ will be equals to half, na? Because normally the operating point is located at the center. You can see that here in the problem itself it is given that the quiescent point is in the center of the load line. Fine. The quiescent point is at the center of the load line, so it will be ICC to VCC upon twice RC, and VCQ will be equal to VCC upon 2IS, or VCEQ, sorry, precisely I will have to write. This is VCC only, ठीक है? So if so, you can see here it is evaluated. IC VCE will be equal to VCC will be equal to half. No, equal to half. So what is the VCC value? VCC value, I think it is given or not? Yeah, it is given. Yeah, it is given in the problem itself. I think it is not mentioned. Please mention it. If it is not, this is a 20 volt. So this is 20 by 2. That is a 10 ohm. Fine. So now you will have to calculate the value of RB. Fine. You will have to calculate the value of RB. So how you are going to calculate the RB? So for that you need the value of some current. I think some current. When you are doing the DC analysis, that time you will have to DC means what? XC will be equal to 1 upon omega C, 1 upon frequency will be equal to 0, that omega 2 pi f, that will be a 0 radians per second. Fine. So 1 by 0 infinity. So this capacitor will not come into the picture, or it will be open circuited. So in that case, this one will be removed from your circuit. Fine. So now you can see that the base current is flowing. The base current is flowing through the RB value. Base current is flowing through the RB value. This is the IC. But before calculating this base current, you need to calculate what? You need to calculate the IC. Fine. So IC, how we are going to calculate? You can see that this is VCE. VCE means this is the operating voltage now, VCE. So just now you have evaluated from the DC load line. Fine. VCE is evaluated from the DC load line, and what will be the VCC? That is the half, because your operating point is at the middle of the DC load line. So VCC will be 10 volt. So now you can see here this is plus VCC, then there is RL, and you are having this plus minus VCE. So what you can do here, what you can do, you can see this is RL, no? The voltage at this point and the voltage at this point. So current will be IC. So IC will be equals to VCC minus VCE upon RL. You can see that the current is flowing from VCC to VCE. Na? The current is flowing from VCC to VCE. So VCC will come first from higher to lower potential. This is VCC will be equal to 20 minus 10. 20 minus 10 upon RL, that will be 100. So 10 upon 100. So I think you are going to have this 100 milliampere is the IC current value. So when I think IC is evaluated, you can simply calculate the IB value. So IB will be equal to IC upon beta, because IC will be equals to beta into IB. Fine. So this is I think this one is 0 0.1, or you can say 100 milliampere upon 100. You can take 100 milliamperes only, not 0.1 ampere. This will create a confusion in the minds of the audience. So I will take this as 100 milliampere, and this one is beta value is 100. So I think 1 milliampere is the IB value. So now IB is 1 milliampere. You can see from the figure itself, this is VCE, and RB is connected between VCC and VBE. So take out this one portion outside, and so what is this is the RB value, this is the RB value, and this one is VBE. So the current which is flowing through the is RB is IB, na? Current which is flowing through the RB is IB. Just a minute, hold on. VBE. So IB will be equal to what? VCC minus VBE upon RB. As VCC is known to you, VBE is known for the for the power for the transistor. Transistor VBE is 0.7 VBE. You take VBE. This you can take this transistor as a silicon one. So that one will be what 20 minus 0.7 upon RB. IB just now know 1 milliampere, so you can easily calculate the value of RB. Uh, so this are the two questions which we have taken. Remaining questions will be taken in the next class. Thanks a lot for your patience.